to this first video in the series on higher mathematics. This is intermediate between GCSE and A-level in terms of the rest of the UK, and would be equivalent to maths in the age range 16 to 18 internationally. This first topic that we're going to cover in the higher syllabus is straight lines, which we of course met at the level below, the so-called National 5 level here in Scotland. And we're just going to continue that topic here. And in 2 tutorials I'll cover this. The first, I'm going to introduce you to 3 useful tools to find the midpoint of a line segment, to relate the slope of a straight line to the angle that the line makes with the x-axis, and thirdly, to find a condition that 2 lines are perpendicular. And then in the subsequent tutorial on straight lines, we will look at triangles and find equations of straight lines for various lines that you can draw within triangles, the median, the altitude, and perpendicular bisector. What we're going to find in the higher series on maths is that we're going to draw a lot on things that we learned at the level below. So whereas in National 5 maths you may feel that it's a set of disparate topics, as you go on with maths, and I think here in the higher syllabus, you'll find that things start to join together and that you'll be drawing on various tools very naturally, and you'll see then hopefully more clearly how and why maths is such an integrated study. Right, let's just dive straight in here. So we want to first of all talk about the midpoint of a line segment. If you're feeling a bit hazy about straight lines, I would recommend that before you continue with this video that you go back and just to remind yourself with the 2 National 5 videos I made on straight lines, just to, as a refresher, would be very helpful. So the midpoint. Let's just make a little sketch here. So there's a straight line. Let's imagine we have 2 points on that line, A and B. There's A and there's B. Let me just give them coordinates for A, x1 and y1, and for B, x2 and y2. And let's call the midpoint of the line segment AB, let's call that C. Now, the coordinates of C are very easy to obtain. If we bring a line down, we can see pretty clearly from this sketch that the midpoint of C will lie midway in terms of the x coordinate between x1 and x2, and indeed that's true, and the way we can calculate that is to simply find the average of x1 and x2, and that will give the value between them. Similarly, for the y coordinate of this midpoint C, that will lie midway between y1 and y2, and we can calculate that by just taking the average of y1 and y2. So in terms of that midpoint of the line segment AB, its coordinates are x1 plus x2 divided by 2 and y1 plus y2 divided by 2. We'll be using this technique in the next tutorial when we're looking at calculating medians for triangles, and so we'll get some practice using that. The next topic is to relate the angle that a straight line makes with the x-axis to the slope of that line. So let me just draw another straight line here. There it is. X and y, here's the origin, and let me say that this straight line makes an angle theta with the x-axis. Just as a reminder, the slope of a straight line is found by taking any 2 points. Let me just take this point here and this point here. And the slope is the difference in the y values, namely this distance here, divided by the difference in the x values between any 2 points on the straight line. Now I want to introduce a bit of new notation straight away. We'll be using this when we study calculus in a wee while, as we say in Scotland, a short time from now. The distance between here and here is the difference in y values between this point and this point. And a symbol we use in maths all the time to indicate difference is this symbol, which is the capital delta. So delta is the 4th letter of the Greek alphabet, and this is the capital delta. So if I write that as delta y, that literally means in maths the difference in and then y. And similarly here, I can write delta x, the difference in x between the x coordinate of this point and that point. That's just a very handy shorthand notation, and so the gradient of a straight line is delta y divided by delta x. We're going to see a lot of this when we do calculus, but it's nice to introduce that right away. Now what's very immediate, I think, and you'll see this straight away when I point it out, if we want to relate this slope of the line to the angle theta, we just have to remember our trigonometry definitions. This is a right angle triangle, and we can see that the tangent of theta is defined to be the opposite over the adjacent. Therefore, this distance divided by this distance is nothing other than the tangent of theta. And so that's a very helpful and important relationship between the angle a line makes with the x-axis and the slope. The tangent of that angle gives you the slope of the line. Now we do have to be cautious if we're dealing with lines that have a negative slope. So let me sketch such a beast. So this slope here is obviously positive, but here now let me draw a straight line with a negative slope. So here this line has a negative slope. We must be very careful that we define the angle between this line and the x-axis to be this one here. It's always the angle between the positive x-axis and the straight line. Now to see why we need to do that is because we always want to say that the slope is tan theta. And if you recall, let me use a different colour for this graph. If you recall our trigonometry lectures, we did quite a few sketches of the tangent of theta. Let me just reproduce that very quickly for you here. I'm going to do it between 0 and 360 degrees just because that was how I was always sketching these graphs when we did trigonometry. But we're only going to need this graph between 0 degrees and 180 in fact. So the line, the function tan theta then looks like this. It starts at 0 degrees, and then it increases positively and diverges to infinity at 90 degrees. It then comes in from negative infinity and goes through 0 at 180 and then goes off. This poor function doesn't know whether it's coming or going. It's so inelegant when compared to sine and cosine, which of course tangent of theta is just sine theta divided by cosine theta. Those are such beautiful graphs with so much symmetry, but this, as the ratio, it does have a lot of symmetry, but it's much less clear, sadly. But what is clear is that this just does just the job for us. If we wish always it to be true that tan theta gives us the slope, yes, we can be very confident so long as we choose that angle theta to be, as I said, the angle between the positive x-axis and our straight line. Why is that? Let's see. If theta is very small, so if the straight line sort of increases in slope from a shallow slope to a very steep slope, theta is increasing between 0 degrees up to 90 degrees. And you see how tan theta starts off small and positive and then goes up to positive infinity. So when theta is 90 degrees, we have a vertical line which has, if you like, an infinite slope, loosely speaking. If we go just a wee bit greater than 90 degrees, and now we have a case where we have a negative slope, just a wee bit greater than 90 degrees, the slope will be very large in magnitude, but negative. And you see tan theta does just the job there. And as this angle here increases well beyond 90, finally to 180, tan theta decreases in magnitude to 0 and is always negative. Perfect. So you see this does just the job for us for all angles between 0 and 180 degrees. We never have to go beyond 180 degrees with this definition, because as soon as we go beyond 180, we're back to this situation again, and we can just define our angle to be this angle that's acute. So, just to recap what we've done so far in this tutorial, simple expression for the midpoint of a line segment, and we have a simple relationship for the slope of a straight line in terms of the angle that line makes with the x-axis, which is it's the tangent of the angle, always bearing in mind we take the angle between the positive x direction and our line. Final topic in this tutorial is a condition. What condition would we place on the slopes of two straight lines for those straight lines to be perpendicular? So let's make a sketch. And I want to sketch two straight lines here that are perpendicular. So here's one, and let me do this the best I can. There's the other, okay? And let's say that they're perpendicular. Let me call this line 1, and let me call this one line 2. And let me say that line 1 has a slope of m1, and let me say that line 2 has a slope of m2. So here's the following statement, very important, also very, very simple. We say that line L1 is perpendicular to line L2 if the product of the two slopes, m1 times m2, is -1. That is the condition for these lines to be perpendicular. And you can say it both ways. You can say if line L1 is perpendicular to line L2, then the product of their slopes is -1. Or you can say it this way, if the product of the slopes of two lines is equal to -1, then those two lines are perpendicular. Now, as you know, if you've been following along with the National 5 tutorials, possibly in the past, the style of the tutorials that I like to give is hopefully, of course, to be helpful and clear, but in addition to that, I never like to make any statement about mathematics and then just say to you, oh, don't worry about it, it's true, carry on. That's not how to teach maths in my view, or physics or science at all. We have to, you must always be a skeptical listener, a skeptical viewer when you're learning these things, and say, well, prove it to me or show it to me. And so a natural question for you when I've made this statement is, well, why is that true? Now, there are ways of proving this which are very straightforward. The really nice, easy ways of proving this actually require a wee bit more than we have right now. In particular, there's a very nice method of proving this using the so-called scalar product of vectors, which we will cover when we do vectors at the higher maths level, but we don't have that piece of maths just now. So what I'm going to do, just because of time, is give you, I would say, a sort of a proof by sketch. If you did this more carefully, you would see that it's actually quite a good proof, but I'll just sketch it for you and you'll see why this is the case. But the general approach in all of the tutorials on this channel is when stating things to give you an indication why that's true, so you don't feel you have to take things on trust. As I've said many times, maths is not like learning a table of, French irregular verbs. It is a network of connected ideas. So that has much more logic and flow to it than something perhaps a bit more ad hoc. Right, so I'm going to give you an indication of why this is true in the following way. Let me draw a right-angled triangle that indicates how we would calculate the slope of line L1. We would say, well, for L1, the slope M1 would just be the difference in y divided by the difference in x. So for the sake of argument, let me just say that this difference in y, I'm just going to call that a, and this difference in x, I'm just going to call that b. So from that sketch then, M1 would just be a divided by b. Now, I'm going to use a compass here to do this really carefully. I'm just going to imagine rotating round 90 degrees here. Okay, there we are. And this point has rotated all the way to here. And my triangle will rotate with it. And this vertical line will become horizontal, and this horizontal line will become vertical. And so here's that same triangle, but now rotated through 90 degrees. Now we know this length is A, and we know this length is B. And now do you see that we can read off the slope of line L2? M2 would be the difference in y, which is B divided by A. But I'm just writing A and B as distances here, and of course from this sketch we see that line L2 has a negative slope, so I must put a minus there. If you were evaluating these slopes from actual coordinates, the sign would work out automatically, but I'm just using A and B as positive distances here. So I have to put that negative sign in manually because obviously this line has a negative slope. So I think from here it's very clear then that M1 times M2 is A divided by B times negative B divided by A, which is negative 1. And so that's a very sort of easy sort of geometrical proof that this is true. So that's the third sort of tool to take from this tutorial, that the condition for two straight lines to be perpendicular is that the product of their slopes is negative 1. And that's that for this first tutorial on straight lines. And as I mentioned, in the next tutorial on this topic, we're going to cover some properties of triangles, which actually is quite a deep topic. You can go a long way with it. We're just going to scratch the surface a bit and talk about medians, altitudes, and perpendicular bisectors. So thank you so much for your attention. I hope this has been helpful, and I'll see you soon.